Welcome to ICE Webinars, a cool place for hot topics. ICE Magazine is proud to bring our monthly webinar series to the imaging industry. ICE is the community that directly links nearly 7,000 imaging professionals with a monthly magazine, online community, annual conference, and now a monthly webinar series. There is still time to register for our 2022 Imaging Conference and Expo in Napa, California next week. This is the only conference dedicated to imaging directors, radiology administrators, and imaging engineers from hospital imaging departments, freestanding imaging centers, and group practices. ICE offers valuable CE credits from the ASRT and ACI, and keeping in line with our successful conferences in the past, offers comprehensive educational opportunities for attendees. For more information and registration, please visit attendice.com. ICE Webinars would like to thank our sponsor, Dunn Lee. At Dunn Lee, they offer services and solutions that meet their customers' needs and help to optimize their business. They do this by offering reliable, quality, and technology differentiating components for imaging solutions at excellent total cost of ownership, as well as by providing their deep knowledge of integrated systems with continued support from product development to after-sales service. For more information, please visit dunlee.com. You can obtain continuing education credit for watching today's webinar. To receive your CE certificate, please complete the post-webinar survey that will be emailed to you 1 hour after the end of the webinar. We're excited about today's presentation featuring Rolf Behling. Rolf, you may begin whenever you are ready.
Hi, good afternoon. This is Rolf Behling calling. We meet in our webinar on a very special topic. Something which is a hassle for many of you, something which is intriguing for physicists. That's what brought me into this, because when I joined 39 years ago, the company Philips, this was a real problem, arcing, or better, X-ray tube vacuum discharges. I've been for 39 years in the industry, head of advanced development, head of process groups, head of field support, so I know the pain of the field. I was a marketing manager, engineering manager, and so on. And today we meet here in this round where I'm now retired and a consultant. So how can you decrease X-ray tube arcing? What's your role there? And what should we know about this? What's known about tube arcing? A little bit about our agenda for this afternoon. We have the problem in practice, which many of you have experienced already, of stochastic breakdown of the high voltage. So suddenly the equipment breaks down like a lightning. And the question is why? And why is it so stochastic, so unpredictable? CT is most affected. Why? We will go through physics models. We will see why this issue still persists after 125 years of X-rays. We celebrate today the 8th of November 1895 when Conrad Röntgen discovered it, and he used high voltage already. Some words about remedies and recipes, Q&A, and if you like, you can also see some literature. In summary, we need high voltage for breaking radiation. Breaking radiation is the most economic way to generate X-rays from medical. And these stochastic discharges occur because there is high voltage. You see it to the right, an anode of a operating X-ray tube, a glass tube. Actually, we can look inside and see the focal spot. We see 150 kilovolts between cathode and anode, and it's just an inch away. So the electric field is pretty high. We will see where the causes are and remedies. It's a little bit intricate, as I said, and there are several models available. We will go through a few of them. We will discuss the value of different technologies, insulation technologies, glass versus ceramics, and so on. We will go a little bit through Dunley's recommendations, and the question would be, what can you do in addition? And I hope that I will be able to answer your questions. The stochastic breakdown is an electric event, and here you see a circuitry of a standard equipment, an X-ray tube attached with a cable to a generator, and suddenly this X-ray tube turns into a switch and short circuits the high voltage. Very suddenly, this creates a voltage surge which moves into the cable back to the generator, and it takes a while until it hits the generator. But on this side here of the generator, the surge reverts sometimes its polarity and moves back into the cable until it again hits the tube. This tube is really a short circuit, only 100 volts difference if between anode and cathode left, because there's really a big plasma cloud then between anode and cathode. It's a short circuit. The tube here conducts about 1,000 amperes in that event. And the surges and cables are creating reflections, ringing. Usually the high voltage can be switched on soon again after the event. So once the high voltage is down, the tube cools down, and it takes less than a millisecond typically that you can switch on the tube again and it's fine again, typically. Sometimes not. And sometimes discharges may reappear. Then the tube must be handled with some care because it may need a reconditioning, or if something has really been damaged, then it has to be replaced. So what we want is that we have no severe discharges which destroy anything. We will sometimes experience discharges, but we want not to make them too heavy. CT is most affected. You see here from a refurbished operation, a CT system without covers, and you see an X-ray tube here. The thing spins. You know that CT is affected because the on time for high voltage is pretty high in CT, orders of magnitude higher than in angio and in general purpose radiography. So the electric fields are on much longer per year than in other modalities. The high voltage is also pretty high. Angio works usually at 100 kV max, maybe sometimes 110, but then the contrast is gone. CT works always, or most of the time, with 120 kilovolts, sometimes 140, and some vendor one vendor dares to do it at 150. So there's a very high electric field generated by the generators. The rotation of the source is one aspect. If you have microparticles in the tube, they can also cause the discharges. We will see that. The temperatures are pretty high. CT operates some tubes to the edge. The gas pressure created by the anode may be pretty high compared to other modalities. And there may be thermomechanical stress. If you operate a tube with 30, 40, 50 patients per day, it heats and cools, so there may be thermomechanical stress and even vacuum leakage that can occur. And there's wear out. Ball bearings at high G forces and the anode also, these things are wearing out and create particles. So what we need is good tubes, not stable with respect to performance. And also what we need is an intelligent generator. We will come to that. So there are a series of physics models available. And you see here a photo of a conference. Actually, this year is this conference again, virtual. This was 2 years ago. Dozens of people working on that field. So klystrons, all kinds of radar tubes, amplifier tubes, accelerator people, they all have the same questions. Where does these discharges come from? One of the models when I entered the company, the only one model actually, was a so-called PASCHEN discharge or gas discharge. People were talking about gas, and you know that a gassy tube may cause a discharge. So that was the only model available then. And it may be applicable if an anode is very hot or if we have gas leakage, but typically the PASCHEN discharge model is not the most important model. The next bullet here is much more important. We think that local field emission, electrons pulled out of surfaces, and the consequences of that, explosive electron emission, is one of the best models which explains a lot of symptoms which we see. It's based on field emission, a little bit on gas and gas sources or vapor sources. And field emissions comes from irregularities. So here we start talking about non-stable stochastic effects, things which get unstable. Another model bases on microparticles, the impact of microparticles on electrode surfaces. And particles are in every tube. Usually they stick to the surfaces, but they can be ripped off in the electric field and bounce around. And also particles from transportation may be there. I recall when in the early days still stationary anodes were used for CT, for this very old Hounsfield systems. These tubes were stationary anode tubes, but once you kicked them by throwing them into a box or something and switching on the high voltage, they started arcing again. And that was due to obviously particles inside the tube. And the last bullet here on this slide is about insulators. So vacuum is only one gap. Vacuum gaps are there, but we have of course also insulators like glass, ceramics, and we have cables and plugs. So we have to deal with all these components here, and probably there are more models. So we had the workshops on that with people who have extremely high electric fields, and then other effects also come in, which may be not relevant for X-ray tubes, but in principle also create vacuum discharges. So still, it is a hot scientific topic. Well, coming back to the very old PASCHEN discharge model, you see here how that model works. It may sometimes occur that we have a real gas discharge in a tube. We call it sometimes gassy. Well, gassy is a right word when the gas pressure is pretty high. What these columns here show is the light effects you generate with a long pipe and electrodes attached to it. And if you raise the gas pressure, so this here is a very high gas pressure, 8 millibars. So the light is not very strong. And if you go down with the gas pressure, the light gets stronger and stronger, and the discharge is getting higher and higher. And if you go to the very low end of the gas pressure shown here, 10 to the minus 2 millibars, these effects vanish. So what is an X-ray tube doing? Well, the X-ray tubes typically have gas pressures orders of magnitude lower than all these gas discharges. We have in a good X-ray tube a base pressure of in the ballpark of 10 to the minus 8 millibar, and which is peaking to 10 to the minus 4 if the anode is very, very hot. If the anode is very, very hot, it creates carbon monoxide, and then the tube gas pressure is rising, but it's still far away from these 10 to the minus 2. It's 2 orders of magnitude lower. So the PASCHEN discharge is not the regular cause of arcing. But it is possible in case of defects. If we overheat the anode pretty much, if we overrun all the specifications and all the data sheets, And then the gas pressure can rise into the -2 millibar range. And also, of course, if we have vacuum leakage, if we have a defect. So this tube here to the right at the bottom was processed, and somehow something went wrong in this exhaust position, and gas went in. And you see here lots of fluorescence on the glass, and also light effects at the cathode side, and the entire tube broke down. And that was really a PASCHEN discharge, a gas discharge. The tube was gone afterwards, had to be scrapped. So, but this is pretty rare. Other causes? Yes, there are. So one of the the best models, I think, is the EEE model, the explosive electron emission model. You see here a tube in operation, a cathode here. The cathode is on. The electron beam hits the focal spot. It's a rectangular focal spot on the focal spot track. And between these two electrodes, we have 150 kilovolts. That is pretty much for this little distance here. And if the tube does not work too well, if the process is not good or the surfaces are not good, then you end up with something which you see here to the right. This is a tube, actually a metal center section tube, where we had removed the anode. But you see here on the cathode a rough surface left. This was polished before. That was nice and smooth. But here at the end, after arcing, the cathode was really roughened. On the other side, and this is depicted here in this tube case in this sample pretty well, because we had a blackening here, a chromium blackening, which is typically rough. But you see here molten spots on these electrode surfaces. And these were opposite to negative surfaces. So the cathode negative, the frame on ground, so in a way, so to speak, positive. And here the features are quite different. It is a bright, large spot, fingernail large, and not roughened as the cathode. So you can see here and identify very easily what the cathode was and what the anode was. And this EEE model very well explains these symptoms. It starts with field emission. This cathode mechanism, EEE, starts with field emission. So electrons are pulled out of little spots on the cathode side. They can emerge from protrusions or even whiskers. The local, we call it work function, may be reduced, so the energy an electron needs to get out, that can be reduced by some chemical effects or other. Inclusions may pollute the surface. There may be some spots on the surface which are not pure metal, but chargeable inclusions. Also, adsorption and desorption of gas has an effect. A gas blanket, we will come to that, prevents field emission or provokes field emission. So that can also change the field emission. And last but not least, if you had a leaking tube and oxidized something, a dielectric layer may build up, and then we have dielectric layer charging and breakdown. So this is the most promising mechanism and explanation for our effects. There are also some alternatives which sometimes happen. This one is the anode mechanism. So this is cathode controlled. Another mechanism may be anode controlled. So for instance, here, returning to our picture to the right, you see here the very hot focal spot. It's about 2,500 degrees. If we go up further, 3,000, 3,200, up to the melting point of tungsten, then we see that plasma can also be generated here on that end if the anode is heated to much. And then plasma cloud can develop from here. Another number 3 effect may be microparticles. So we will see in a minute how that works. Microparticles may bounce back and forth between anode and cathode, and they may also create little discharges because they bring charge, and if they approach a surface, they may trigger discharges, which then in turn release lots of energy, such that a big discharge may occur. This is a rare event, but it happens. I think it happens predominantly if these microparticles are charged and dielectric and not metal, but well chargeable, like metal ceramics dust or glass dust or whatever. But it can also be that metal particles do it. And then we have insulator breakdown and, of course, external cable issues. So this is a series of models which are most probable. It's a mixed effect often. Sometimes the tube starts with a cathode mechanism, then experiences also microparticles, because after a discharge, particles are released. An insulator may be deteriorating, and again, also from all these events and so on. So it may be a mix of effects even in a single tube. Coming back to this local field emission, which causes EEE. Here I copied and I've stolen a picture of a book from Latham, a very nice one. I could, it would be great to read that for you. Latham in 1995 already, he depicted a vacuum gap, plus, minus, and black in between. Nothing in between, fine. 35 kilovolts applied, very narrow electrodes, okay. What he saw was that in the next step, some nanoseconds later, a cathode flare appeared. So the cathode started with something on 2 spots, left and right. A little later, the anode responded. So here you see plasma and intransparent material. So and bright light from this material in his camera. And you see that the cathode goes up with its activity, and the anode responds. And then finally, this is the picture of the total short circuit. Here on top, we have microamperes. Here at the bottom, we have kiloamperes or hundreds of amperes. So typically, the cathode starts with its activity, and the plasma clouds builds with about 10 to the 8 centimeter per second and expands with its speed into the vacuum gap. And after preheating, it may also come from the anode. So this model explains multiple symptoms, and we will see. So this is a packed slide. The picture is a little bit cramped, but I thought it would be nice to see it. It's a copy of a book here. This is about field emission. Classically speaking, classical physicists would say, no, field emission is impossible. It is absolutely impossible because you cannot pull an electron out of metal. It needs energy, for instance, 4.5 electron volts for tungsten to get out. And where does it get from? Light is not there, it's too low in its energy. But quantum mechanically, it can happen. So this picture shows a wall between left tungsten metal material and right vacuum. And the anode is to the right. And in between is an electric field. And if you probe an electron and move with an electron from left to right, the electron is typically at the Fermi edge of the conduction band. And if you if you manage to get it out somehow, it sees the pulling electric field of the anode. So if it manages to get out, it falls into an electric field and travel to the anode, running down this slope here. As I said, classically speaking, this is impossible, but quantum mechanically, the electron can borrow some energy pass this tunnel, and then get out. So field emission is a tunneling event. And this complicated equation shows the exponential rise of the field emission with the high voltage. So every tube, every X-ray tube has field emission. There's no way out. Some have microamps, some have 100 microamps, but there's always field emission. There's always weak spots in X-ray tube. Well, theory tells that that such an electric field here can pull electrons out of ideal surfaces, but theory says that we would need 3 megavolts per millimeter to pull an electron out. So it's impossible. We don't have this. We experience field emission already at 10 keV per millimeter. Why that? That's orders of magnitude lower. Another thing which is curious, which is a little special, field emission sites seem to be very local. If you make X-ray imaging of field emitter activity, these things are very local. And it seems to be that irregularities weaken the electrode surface. Protrusions, impurities, inclusions, microparticles. And that's shown by the next slide. Also stolen from Mr. Latham. Here are some irregularities shown. Protrusion, the dielectric inclusion here. Dielectric because that's dangerous because these things can charge. Oxide and inorganic dielectric films. Gas layers. So grain boundaries with inclusions. And all kinds of microparticles and products from oil, cracking oil here, so blankets of some dust, then residuals of prior discharges, craters and what have you, and also voids and pores and cracks. So field emission is created by all kinds of irregularities. What we have to know is that protrusions enhance the electric field at their apex. So the height and diameter ratio determines the amount of electric field enhancement. And the enhancement is typically by regular protrusions only in the ballpark of 10. What we measure from our field emission curves is that it is higher. It is typically higher than the 10, maybe some 1,000. So that points to the fact that other irregularities, like the ones depicted here, are also relevant. So the aim of the process and tube manufacturing is minimize field emission. This is an interesting thing because a figure from or a graph from Mr. Juttner in 1990 in East Berlin. We were attending the same conference and he presented this chart here. It's interesting because it relates field emission centers to gas. We talked about gas. What he did was let field emission run. 250 nanoamps, not much, a tip of tungsten. And then here he put in, he raised the pressure of argon. And for some minutes, he let the field emission act and measured the field emission. And what it did rise quite a bit by a factor of nearly 10. So why was that? His explanation was, hey, there is gas on the surface of my tungsten tip. And as soon as I remove the gas layer by sputtering with argon, then the field emission center starts sending out electrons. So there's a blanket of adsorbed gas, which is fine, but it's not stable. Once you sputter it away, field emission rises. So this is triggering then EEE as a stochastic effect. Is there another proof that his theory is right? Well, he switched on, or he turned the valve off, turned the argon off, the pump put it out, and then he measured field emission again. And you see here that the field emission dropped down to the old level. And the time constant here was exactly the time needed for the gas, for the residual gas of carbon monoxide, or what was it, to be reabsorbed. So ion sputtering removes the blanket, and this destabilizes the field emission setter. This is, again, a stolen chart here from Mr. Fursey, his work. And Fursey, in message to Russian physicists, explained this EEE effect for the first time. Well, these are cartoons. They are not really physics theory, but they show what this is all about. Initially, we have field emission. The field emission is more or less stable, but once the emitter gets a little unstable, it heats up and starts evaporating. So it sends gas into the space. This gas is subject to electron bombardment, turns into ions. Ions go back to the origin of the field emission, heat up the surface, and energy is put into the field emission center or its environment. So the surface liquidizes, and that creates more electrons because the liquid is pulled out of the surface. Craters form, and protrusions feed electrons. And suddenly a plasma cloud, and we switch to the right, here's a plasma cloud expanding. This plasma cloud is very dense, very hot. It has a pressure of 10 kilobar and goes and bridges the gap. And once it reaches the anode, the gap is bridged and we have high voltage breakdown. So the leftover here is craters, exactly what we saw in our tubes. Here's a picture of that. This is a picture. You can find it all over in every X-ray tube you open. If you look into a scanning electron microscope, and I did this last year, this is exposures from that, you see craters on the surface. They're pretty small, 50 micrometers, this bar here. If you look into the craters, you see different sizes of craters. One is large, the other ones are smaller, and in the middle of the large one, we see that there was an inclusion which contains chloride. So this is not good because it is a chargeable inclusion here. So once we have a big discharge, it can expand into small ones. So you see often traces of discharges. And the residual gas atmosphere contributes, and also nanoparticles on these surfaces contribute once they are subject to ion bombardment. So material preparation and vacuum quality are really key to prevent this. One word about microparticles. As I said, microparticles can detach in vacuum. They sit on a surface with van der Waals forces, and you have to wipe them off if they want to clean the surface. But also electric fields can pull these microparticles off. Here you see a 150 kilovolts anode and a cathode at ground potential, and this little particle is charged. If it sits on a neutral or a equipotential here, then electrostatic theory says it is charged. It has this one here has about 10 to the 4 electrons in it. And then this thing is, of course, subject to force. It's pulled off if it's large enough and the sticking force is not good. It's pulled off, moves to the other side, returns and swaps its charge, and bounces back to the anode, and it gains energy. And Mr. Kronbeck in 52 said, well, if the particle hits a surface so hard that the surface is damaged and evaporates, then we have what we're looking for, plasma, or vapor turning into plasma. So this theory is, it's a little bit tricky. I don't want to go into more details, but at least some particles, if they are large enough, can create arcing with some kind of this process. So the arcing rate in tubes may rise from wear out of ball bearings, of anodes, and of other stuff. Now we have not only vacuum in the tube, we have also insulators. And here you see what an insulator does when it's subject to electric force. There's a tricky point in an insulator metal combination, the so-called triple point. This triple junction here connects vacuum, an insulator, and the metal. The insulator wants to get rid of its electric field due to its dielectric constant. It pushes the electric field aside, and if you have a little void here or some irregularity, electric field is enhanced here and creates field emission. Once field emission appears and hits the surface, this insulator charges. You would think it charges negatively. No, it charges positively because under certain regular circumstances, one electron going out and hitting the surface creates multiple electrodes and ionizes the surface. So instead of getting negative, the surface gets positive and increases the field emission here from this spot. And that may create a flashover, and in some cases even a puncture if the charge accumulation is too high. So the insulators, going back to our bullets here, are maybe ionized during electron impact, but also ion impact, vacuum ultraviolet, and X-rays. And the ceramics doesn't forget easily. It stores charge. So once the tube has a history of this, the ceramics is in a different situation than before. And charge multiplication causes field enhancement at triple points. And in the end, a flashover ends up with a reduction of alumina. You have aluminum left and black spots or traces. So the tube may survive such a thing, but the arc rate may rise if once a trace is on an insulator. So this thing is lethal. If an insulator is really punctured, we have to replace the tube. The tube must be replaced. It's not reversible. Comparison of technologies. Let's have a word on that. Glass versus ceramics. Well, you see here a glass tube in operation on an exhaust position, and what you see here is the blue curl. It is a sign of electron bombardment of the glass. So how can glass be bombarded? It charges. Yes, it charges, but it discharges also because electrons multiply and they get off again. So there is a current. There may be a current flowing through the glass or on the glass and back. Also, ions may be here. So if a glass tube is in heavy ion bombardment and electron bombardment, the glass is subject to currents, and that's not good because the glass is not very stable. It is brittle, it is fragile, and if current flows over glass, it may break and implode. The other thing is that glass charges are poorly defined. They can turn from very positive to very negative, depending on the events. So you need always a surrounding and an environment, the casing, far away to be prepared for all these situations. So you need a large tube housing to house a glass tube. And also, last but not least, the glass is subject to coating. Typically, it is around the anode and the cathode. So it's coated with tungsten from the anode and also from the cathode, evaporating cathode. Ceramics, on the other hand, is much more compact. And here's the first metal ceramics tube when I joined Philips in 1980. We had trouble with this one here because this ceramics was not easy to process. But we put the ceramics far off the focal spot. We put it in, we shaped the triple points well, and we called it here the field guidance. We needed a photon shield, and the benefit of ceramics is very robust and stable. Once it works, it works. So this is a more reliable and stable technology for long-living tubes. Glass is a little bit more sensitive. So introduced in 1980, but now considered the best technology available, and all the other vendors, Siemens, Varex, GE, and many others use now metal ceramics technology. Here, and we were coming to an end now, showing a chart from production, but the same thing is also in practice visible. So what this chart shows is a rising voltage. So we do it in processing to degas a tube, electron bombard a tube. So the voltage is rising, and what you see here at that doesn't go smoothly. So once you raise the voltage, the tube starts spitting and having discharges. This is visible here in the gas pressure. Here, this tube is still on the pump. You can measure the gas pressure, and every discharge here creates a spike in the gas pressure. These are the current curves, anode cathode current, but you see it also here in this event, in this gas pressure. So this is from processing. We process tube. The tube learns to live with a high voltage because once you have conditioned it and reduced the voltage again, the arc activity decreases. So the progress over time, arc rates have significantly decreased in the past. Processing is better, material and conditioning is better. Robust metal ceramics technology has been introduced. And last but not least, we offer intelligent generators. That's why a package of generator and tube is so important. An unintelligent generator switches just off, and if a tube spits a little bit, breaks off the exposure. This is not good. Modern generators switch off temporarily for a short period, let the gap cool, and switch on again. And the operator doesn't have to do anything. And the operator will sometimes not even notice. So multiple discharges can occur in an exposure without noticing it. But that requires intelligent generators. No? Yeah, if a tube is under operation, what we have to do is handle it with care. Don't overstress the voltage ratings. Use moderate currents, no overheating, and in some cases, it is advised to recondition the tube. And you see here the last voltage is a little lower than the previous, and you see already an improvement. This is part of the conditioning process. The tube arcs heavily. The arcing is here damped by a resistor. So this is not an intelligent circuitry, it's a dumb circuitry, but it works well. A resistor is not possible in practice, but in this processing step here. So the resistor switches off the voltage and returns the voltage soon after the discharge is gone. And the tube learns, and that's what we can do also in practice. Yeah. Installation and tube replacement has to be well done. Here you see what happens if the plug is not well inserted, and that's of course a more trivial thing, and we will, but we have to avoid that as well. No. Yeah. So in the end, what it's advised: buy a reliable product, a good one. Observe generator compatibility, and adhere to the recommended procedures. Warm-up procedures. In the past, warm-up procedures were warm-up procedures to warm up anodes, which would be brittle otherwise. But that time is over. Tungsten anodes are not existent anymore. The anodes are got much stable, but the terminology warm-up still is there. What it means that voltage is applied, moderate voltage, a certain gas level is there, so that gas effects can also act on field emission centers. So the tube learns to live with all these circumstances and gets stable. And after warm up, you can then rise the voltage carefully to the operational voltage. Thank you very much for listening. I hope I was able to give you an impression about tube vacuum discharges or arcing. Well, it's typically is not really arcing; it's vacuum discharges, but arcing is a kind of slang in our industry. So let's call it arcing. Thank you for listening, and we like to prepare ourselves for questions and answers.
Yes, Rolf, thanks so much for the presentation. We did have a couple of attendees that submitted questions, but before we get to those, I want to remind everyone you can still submit your questions for this live Q&A portion of today's webinar by using the question feature on today's dashboard. We're going to try to get through as many as possible. If there are any that we cannot get to due to time limits, then we will certainly send them over to Rolf so he can follow up offline. But with that said, Rolf, the first question, after replacement for arcing, the new tube is not better than the old one. Should I return it?
Give it a chance, I would say. A new tube is always a little bit more unstable than a tube which has been in operation for years. One of the reasons is that the gas pressure inside a tube, believe it or not, is better when the tube is old than it is when it is new. There's a very efficient pump inside. The electron beam ionizes the gas and removes it, and the gas is buried in the cathode. So give it a chance. Recondition the tube moderately. Some tubes learn pretty fast, some not. Only if the new tube has really a damage, if something broke off during transportation or so, then you need to return it immediately. But otherwise, it takes a while. Apply the recommended procedures.
Next question, why do people call arcing tubes gassy? How much gas is in them?
Yeah, we touched it already. It's not much gas, only if defective tubes have a vacuum leakage. The gas level is high. Otherwise, the tube seems gassy because the arc rate is high. And the old terminology says, well, it seems to be related to gas. That's the model of the PASCHEN discharge, of this gas discharges, but it's not really true. High gas pressure can destabilize a little bit, but the impression that there is a thick gas cloud inside, that's not realistic. It's more complicated, more sophisticated. The modeling is not exactly like that.
The next question is, can you build a totally arc-free tube?
Absolutely. That's no problem. Just triple the size of the anode cathode spacing. We have done this in one tube series, which is now a good platform for CT. We just doubled the size of the insulators, and the effect was beautiful. The arc rate went down. But it is not practical because we need compact devices. We have to spin them on gantries with speeds of 4 revolutions per second, 30 plus G. And we have to have angio systems which do not bear too large tubes because the operator has to move them around. They have to be flexible. So the tube must be compact. And of course, the price is also an issue. A large tube is of course more expensive than a small one. So it would be possible, but this is a kind of trade-off between little arc rate and compact design.
Sure. And a couple of additional attendee questions to get through. When a tube starts arcing, can it be degassed?
Yes, it can. It can. Let the pump work. The vacuum pump inside it's an ion getter pump, so to speak. If you run the tube with moderate or low voltage and raise the current in the tube, the ionization effect is pronounced. So you see that the ionization, the rate of ionization is proportional to the electron current, and it is rising when that voltage is not too high. So degas the tube with moderate voltage, let's say a CT tube at 80 kilovolts or something, with higher current, and then the gas is removed and is buried in the cathode. Also, parts which may be able to gather the gas are metal which is susceptible to gas adhesion and chemical reactions. They also act as a getter and reduce the gas pressure, and this in turn reduces the instability. We saw this thing with the sputter effect of Jüttner. The instability is getting less severe then. Other effects are buildup of gathering surfaces. The anode is evaporating a little bit, the focal spot, and that creates active coating inside a metal ceramics or metal center section tube, and that is good for gas absorption.
Another attendee would like to know, how can I determine the vacuum is low? Why is it caused, and how could I resolve this problem?
You mean the vacuum pressure is high when the vacuum is low, I suspect. There are several options. If we have an oil leak, high oil pressure in the tube is also creating a deterioration of the emitter, of the electron emitter in the cathode. So the tungsten wire carbonizes, raises its work function, and the emission goes down. So oftentimes when we have a leakage, we see reduced emission current. Otherwise, it's very difficult to see the gas pressure right away. There are some measures that you can switch a tube, rewire it so that it becomes a gas gauge. If we use grid switch electrodes and stuff, but that's not very easy, and that's not possible in the system. What is also possible is if a tube is very gassy, if the gas pressure is very high, you sometimes see runaway effects, that the emission rises when the tube gets hot. That depends a little bit on the removal of space charges in front of the cathode. So if there are lots of ions, the space charge goes down, and then the emission goes up. So this is also a sign of high gas pressure in the tube.
Another attendee would like to know, at what age would a tube start arcing?
Unfortunately, it can start already at an embryonic stage. Typically, this should not occur if the calibration procedures have been worked through. It should not do it. In the end, it may start arcing when, for instance, the pollution with microparticles goes up. Worn out bearing systems, worn out anodes. So for instance, if the focal spot track gets really roughened and particles fall out of the focal spot track, tungsten microparticles, then they may create arcing upon the impact on electrons. Another cause may be in glass tubes, the coating of the glass. The buildup of little coating, let's say a monolayer, is not critical. But once the coating by tungsten or other metal from discharges, for instance, on the glass deteriorates the glass insulation capability, so the glass becomes conductive. And then also this conductive layer becomes an electrode which partly shortcuts the intended insulation gap. So in that case, a tube can start arcing as well. So at the end, a tube may fail by arcing due to all these fatigue processes. If the tube is run smoothly and with not excessive power ratings, then it can work well, because as I said, the gas pressure even goes down instead of going up.
All right, Rolf, I think this will be the last question that we have time for today. Which is safer for a tube during a scan? Volume scan continuous or axial scan flashing?
That's not much difference. Actual scan, well, the first instant of high voltage on is a little bit critical. If you have had a break, if the tube set idle for a while, and then you switch on, what happens? The anode is covered with gas. Adsorbents, if the anode is cool, adsorbents cover the gas, the anode. And in that case, if you switch on high voltage, this gas layer is removed in the first revolution of the anode, because the focus spot is heated immediately to 1500 or even up to 2500 degrees. So this layer is removed, and this gas is then in the tube. For the next scan, for the next scan, the gas pollution is not that severe. So in that case, I don't see any major difference between both modes of operation.
Rolf, I want to thank you one more time for a great and a very informative webinar today. And thank you again to today's sponsor, Dunley. I encourage all of the attendees to visit their website, dunley.com. Just one more reminder that the post-webinar survey and the certificate process is automated. So the survey link will be included in a follow-up email, which you will receive in about an hour's time. Once you have completed the survey, you will be able to download your certificate immediately. If you have any questions, please contact us at webinar@mdpublishing.com.